Hi. So what we want to talk about now are our functions, are the sort of the things that act on sets. So um, the point about functions is that they are how we describe what sets do. Okay, so let's see. Galileo is the we'll start our story with. So this is a picture of somebody who's supposed to be Galileo, and he's rolling balls down the inclined plane here. So he's expressing the relationship between the time passed and the distance fallen. He's got a ball and he's going to roll it down. So he's going to get a chart that says for 2 seconds it's fallen this distance, for 3 seconds it's fallen this distance, for 4 seconds it's fallen this distance. Okay, so that is to say that that we're seeing a relationship between a time and distance. At first, people thought about how inputs determine outputs in terms of formulas. So, for example, in 1718, Bernoulli described a function as an expression made up of a variable and some constants. And similarly, in middle school, you begin learning about things like x squared minus 3x plus 1, and you practice, what happens when the input's minus 2, what happens when the input is minus 1. However, pretty soon the limitations of that became clear. So an example is an important application in physics. Here is a string. If you pluck this, then what you'll get is the pluck will travel down the string and come back. D'Alembert pointed out that we can form the initial pluck in any shape we want, and it'll travel as a body down and come back. That is to say, the solutions to the relevant equation aren't necessarily those things described by formulas. You can pluck it in any shape at all, whether it's a formula or not. So we can't expect that the string will only take those shapes that can be described using addition, subtraction, trigonometrics, etc. So that is to say, in summary, some functions, some input-output relationships are described by formulas. That's great. F of x equals 2x computes the input-output relationship. Input of 0 is associated with an output of 0. Input of 1 is associated with an output of 2, and etc. But for some functions, there's no obvious way to see it as described by a formula. So if, for example, I take the function that associates an input year with an output of the team that wins the World Series in that year, it's just not sensible to say there's a formula for that. So a function is a set of ordered pairs. Doesn't say a set of ordered pairs given by a formula. It says a set of ordered pairs, input, comma, output. Now, the ordered pairs are subject to a requirement. The requirement is called well-definedness, that if you have the same input, if you have x for an input, and you write down x comma y0 and x comma y1, then y0 has to equal y1. In other words, the same input always has to give the same output. So a function is required to be well-defined. The definition is perfectly general. It doesn't say that the inputs and outputs have to be numbers. They can be integers, but they can be vectors, they can be strings, they can be anything alike. And again, the point of well-definedness is that if f of 7 is 49, then it can't be the case that f of 7 is also 48. That just violates the definition of a function. Okay, so a function is an input-output relationship subject to the condition that the input determines the output, completely determines the output. So time for some examples. Okay, so here the second number is the square of the first. So the function is written as the name equals a collection of ordered pairs. It's not maybe the most familiar way to write the function, but perfectly legal. 0 is associated with an output of 0. 1 is associated with an output of 1, but 2 is associated with an output of 4. That is to say, the input squared makes the output. So it's perfectly fine for the input-output association to be describable by formula. That's fine, but it also has to be perfectly fine for it to be not describable by formula as long as the output is determined by the input. Another example of a function is that the distance between 2 points in the plane is determined by the 2 points. So here the distance would be ordered pair. See the ordered pair open paren and the ordered pair closed paren? And there I've got p comma q, so that's the 2 points. And then it's the familiar Pythagorean distance formula, p0 minus q0 squared plus p1 minus q1 squared, all take the square root. The identity function returns whatever you gave it as input. And finally, for a more general function, everybody has a mother. That is to say, for each input person, there is an associated output mother. The thing about functions is that the way to think of them is that functions are actions. So whereas sets are the things on which actions occur, functions are the actions that happen to those. So for example, functions can pick out or name things. Functions can impose an order, all kinds of things like that. So here's an example. I want to pick out the winner for the American League and the winner for the National League, I wish. So here the American League winner is the Red Sox and the National League winner is the Cubs. I've picked out the Red Sox and the Cubs. Suppose I take the set Carol, Alice, and Bob, and it's unordered. If I want to impose an order on the set, then I can have a 1 associated with Alice, a 2 associated with Bob, and a 3 associated with Carol. And now the set is somehow been put into alphabetical order. So functions are actors. Non-functions. So what's going on here? I'm having a little trouble with the PDF reader. There we go. Non-functions. So for example of a non-function, sometimes it's easiest to understand what something is by understanding what it isn't. So the curve y squared equals x comes up in calculus. So here it looks just like x equals, excuse me, it looks like y equals x squared, except it's been turned on its side. This is not a function because if you give me, for example, x equals 9, it is associated with 2 different outputs. That violates well-definedness. X of 9 is associated with a y of 3 and also associated with a y of minus 3. That violates the well-defined condition. Calculus texts give the vertical line test. You may remember the vertical line test of whether y is a function of x. You slide a ruler across the graph from left to right. The graph is a function if and only if at each point the ruler intersects the graph in exactly 1 y. So let's do that on a piece of paper here. So if I draw the graph I just had, oh, bugs. If I draw the graph I just had, this is the relationship. It's all the x comma y's where a y squared makes x. And if I draw some vertical lines, vertical line, vertical line, vertical line, it's easy to find one, this one right here. It's easy to find one where the vertical line crosses the graph in 2 spots, not 1. So because the vertical line crosses the graph in 2 spots, this is not a function. Oops. Oh, I'm having a lot of trouble manipulating the screen here. An example of something from practice that a person may be familiar with that is not a function. It's a perfectly sensible thing to look at in a textbook. For example, a hysteresis loop is that when you give the field strength, you can't tell the magnetization. If I tell you the field strength, you can't tell whether it's this magnetization or that magnetization. Okay, another example is in a database table. If I have name, comma, email address, the name doesn't determine the email address because people can have multiple email addresses or maybe no email address at all. Likewise, the email address doesn't determine the name. When you have a database table where one of the entries determines others of the entries, that's a very important entry. You might call that a key. But so the point is that this functional relationship is very useful. But in an ordinary database, name, comma, email address, neither one determines the other. So it's not a functional relationship. The association between month and number of days in the month is not well defined because if I ask you what's the number of days in February, you'll say, well, sometimes February has 28 days and sometimes it has 29. So one of the things that we will want to talk about is how do you spot when you have a function. A function is a set of ordered pairs. That usually won't give us too much trouble in association between input and output, but it's subject to the condition that the input determines the output. So the first example here is string length. Well, if you give me a string, it has a determined output. Jim has length 3. OK has length 2. SMC has length 3. The empty string has length 0. So every string has a length, and furthermore, no string has multiple lengths. A human resources database might contain a table with entries like social security number, name, and monthly taxes. Now, the point of social security number is to make functional relationships. The point of social security number is, unlike, say, the name John Smith, there are not supposed to be 2 people with the same social security number. So the Social Security number determines the name, and the Social Security number determines monthly taxes. That is to say, Social Security number is a uniqueifier. Okay. However, you can click on that link in the slides yourself. It turns out that the question in practice is more complicated than that. So some words, and some of these are probably familiar to a person, some words may be less so. The domain of a function, DOM of f, is the set of possible inputs. The range of a function is the set of outputs associated with those inputs. So for example, the string length function has domain, that's the set of all strings, including an empty string, and its range is all the natural numbers, 0, 1, 2, 3, because if you give me a natural number like 104, I can find a string of length 104. The usual squaring function, x is associated with x squared, has domain the real numbers, and the range is the real numbers greater than or equal to 0. Restrictions. So we sometimes have a function and want to limit its domain in some way. So for example, suppose that the function f has domain D. If a is a subset of D, then the restriction of f to a, denoted with, this is called a harpoon, f harpoon a, is given by that f harpoon a is of f harpoon capital A of lower a is equal to f of lower a for all lower a and capital A, and it's simply not defined if lower a isn't capital A. And why would you want to do such a thing? Well, we often want to do such a thing. You might, for example, want to look at the square root function and not allow yourself to try to take the square root of a negative number. Another example is, recall that the domain of the cosine function is the entire real line, but when you work with the arc cosine function, we often want to restrict so that when we take the arc cosine of let's say arc cosine of 0.6, we only allow as outputs those angles that are in a certain range, say from 0 to pi. At least when I was in high school, we denoted the restriction of the cosine function to the range from 0 to pi, to the zone from 0 to pi, with a capital C. It's called the principal value of the cosine. So you sometimes want to look at a function that is restricted to some subset of its sort of original domain. And codomain. We often don't use the range when we're talking about a function. We often don't use the range and instead use a convenient superset. And the obvious example here is f of x equals x squared. If you're a programmer and you're writing code which is supposed to return the square of its input, then you probably would declare it this way. This is, I've been told, is the Java way to declare a function that squares its integer input. Notice here that I'm returning integer, even though this function doesn't have a range of the integers. It has a range of the positive integers, non-negative integers. So you probably would not, though, declare that what it returns is a non-negative integer. You probably would just say integer. That is to say, integer is a convenient superset of the range, and because it's convenient, we use that. In that context, we say integer is the codomain. It's a convenient superset. Let's take another example, the DNS. When you go to your computer, you go to your browser and you type in some address, like joshua.smcvt.edu, then it gets translated to 192.80.64.209 to the dotted quads. Now these associations between names and dotted quads change all the time. Websites are appearing, disappearing, addresses come and go, sort of stuff. So specifying the exact range, which dotted quads are in use at exactly this moment, is basically not possible. So instead it's convenient to just say it could be any dotted quad. It's a convenient superset of the range. So the convenient superset of the range is called the codomain. When we define a function, we often write f colon d arrow c. D is the domain, and C is the codomain. So here we have some dots in the domain, and they're being associated over with dots in the codomain. And you notice that I didn't write the range up here. I wrote the codomain. I wrote the convenient superset. Okay, so codomain might be less familiar to a person, but maybe we're back now on more familiar grounds. If I look at a function like h of x equals sine of x squared, that's a combination of the squaring function and the sine function. It says do the squaring function first and then do the sine function. Okay, so the combination of two functions is called a composition. The composition f circle g, I read that out loud as circle. You could read it as a composition of f and g, that's fine, but I read that out loud as f circle g. The composition f circle g of f and g is given by the input x is associated with the output f of g of x, where it makes sense. This picture. Here is the domain of g. Here it's the codomain of g, but it's also the domain of f, because what comes out of g is going to go into f. And then over here is the codomain of f. So that's what it says down here. G maps D to B, f maps B to C. Now notice, there may be some things over here that are inputs to f that are never output from g. That can happen. So you can end up bouncing over and entirely missing some things. That can happen. Where it makes sense means that the range of g has to be a subset of the domain of f. What if we had an arrow from this domain here that went off into space and is not something that makes sense to input into f? Well, then the definition of composition would be in trouble. So where it makes sense means that the range of g has to be a subset of the domain of f. So you think of f circle g as meaning f comes after g. You do g first and then you do f. So 2 quick examples, and then that'll be enough to do some practice homeworks with. So imagine, for example, that you're building a web page. You have a form field for last name that allocates 20 characters. So then consider the length function, which takes strings and returns integers, natural numbers, and then consider the true false, the verification function that takes in integers and returns true or false, given by a t of n is true if n is less than or equal to 20 and t of n is false otherwise. So exactly what we're interested in when we're trying to verify that the last name is indeed less than 20 characters is we have to first compute its length, and then we have to decide yes or no, is it a length we can allow. So we're taking compositions of functions all the time. One more example. Our human resources database could contain a table with entries like social security number, name, monthly taxes, and another one that has entries monthly taxes, payments due at retirement. And with those two tables, we can start with the social security number and determine the payment due at retirement. You go from social security number to monthly taxes, and then you go from monthly taxes to payment due at retirement. It looks just like the picture on the prior slide. You go from social security number to monthly taxes. You go from monthly taxes to payment due at retirement. So that's a composition of those two. Okay, so very good. So we have the introduction to function. The key idea here is that a function is not a formula. A function is an association of input with output subject to the well-defined property that the input determines the output. And we're going to practice this with some homework, and then we'll come back and do some more sort of advanced function stuff. Okay, see you.